From game development to high-frequency trading, thanks to QDC, the Quantitative Developer Certificate.
Good afternoon, everyone. My name is Tesch. When I don't fly a starship, which unfortunately is most of the time, I teach C++ algorithms, computational system fundamentals, and retro console and emulator programming, that's a new one, to aspiring game dev students. Some contact information is there for both my organization and me. Don't be afraid to hit me up on LinkedIn or send me a mail. I am very open to talking. Some good news too. The people from Pact asked me to distribute a book. I have several of them. So if anybody asks a particularly smart question or gives a particularly smart answer, you are getting a book for it. I actually bought the same book here from the thing a couple of days ago, so I could have stolen one for me, but it's too late now. I have to mention that I don't officially endorse the book. I have, because I'm jet lagged, read 2 chapters of it, and it's okay. Okay. Writing the world's fastest GameBoy emulator and modern C++. First question is, why? Why? Well, I kind of want to break up my answer into several parts of that statement. Why modern C++? Well, this is C++ and we're at CppCon. I thought you wouldn't be that interested in if I tried to write the fastest one in Java. I didn't want to do that either, so we're fine. Why write an emulator? As a programmer, I feel that, and I notice that with my students as well, some of them have written emulators or part of emulators for their grad work, and this gives them much deeper understanding of the hardware. If you have to emulate the hardware, you have to understand what the hardware does. The whole mystery of I put my C++ into something and actions come out becomes, no, I understand what these steps do. Okay. Wow, 2 words in, we're doing great. Game Boy. Why the Game Boy? By the way, happy birthday, Game Boy. It was launched in the US 25 years ago. So a quarter of a century. Who ever played on a Game Boy? That is great. That makes this talk a bit easier. About 120 million were sold. 197 million if you include the Game Boy Advance that was backward compatible. And it wasn't really backward compatible. There was actually a Game Boy built into the thing. So 200 million, more or less. They were up to the PlayStation 2, the best-selling console of all time. But now they're the 4th or something. Still, a very important piece of technology. It had a terrible screen. People who say it's not true, it's been a long time since you played one. I have several. The original is terrible. That screenshot is really well taken. I found it on the internet. I don't know what they did with the lighting. When it starts moving, everything blurs. So the resolution is pretty low. It has 8 buttons, a D-pad, start, select A and B, stereo sound via the headphones because it's a mono speaker. Since you all know what it is, there we are. So it was important. It's pretty simple technology. Screen is not too high resolution. Those are advantages. A lot of people have noticed that it's easy to make an emulator for a Game Boy. If you want to write your own, you will not be the first. There's a lot of open source there. That's a great advantage. If you get stuck somewhere, you can look up how other people did it. There's also a plethora of technical information available, very detailed. We all wish we had this. I don't know how many of you went to the unit test talk. The person who gave it was a great talk. And he said the most important thing you should take away is you need to write unit tests. That is true, we need to write unit tests. Who doesn't write unit tests? A bunch of liars in this crowd. For hobby projects. Good news is, the Game Boy has a bunch of test ROMs. It's not as good as unit test, but still, right? You put that into your emulator. If it works, you know where you stand. It actually gives pretty detailed information about what went right or wrong. So that's all in all great. What else is great? Well, it has a huge library of games. That's interesting for what we're going to do with it eventually. And also this huge library is tiny. No, I haven't lost my mind. It's tiny in size. The entire 1,000 games fits into 800 megabytes, which makes it reasonable to do stuff. How much fun can you have with just 800 megabytes? Well, quite a bit if you have a GameBoy emulator. There's also, surprisingly, I looked up the numbers this morning, a very active homebrew scene. There's this little graph there. Blue is for original Game Boy. There's 807 homebrew projects available online. So on top of those 1,000 games, on top of the 30% of those 576 that are backward compatible, all these games are there for you to enjoy. Some of them are shit. Not all of them. These homebrew projects, sometimes it's also just a demo or something. Well, I say just a demo. The demo can be really interesting. It's like the Commodore 64 demo scene. People do crazy stuff with these things. Also important when you make an emulator, it's actually quite simple. The Game Boy was launched at the end of the 80s, actually after the 8-bit period. What does that mean? It means that when they were designing it, everybody knew a lot about how to design a good and clever 8-bit system. And that's why you get such a clean design. If you look at the PCB here, I have some labels on it. Yeah, it can't be much simpler than that. All right, some RAM, some VRAM, and then everything connects to the connector, and mostly you're there. There's almost no other chips on there. Why is that? Because way ahead of its time, this was a system on chip. It had built-in a graphics device. Nowadays, we would call that the GPU, but then it was called the PPU, the pixel processing unit. The clock frequency was 194,304 hertz, or 4 megahertz. That number seems special. Does anybody know why it's special? Is that what?
Relevant.
What?
PAL or NTSC, I know the
It's not related to PAL or NTSC. Actually, the Game Boy is not region locked. You can buy them from anywhere. The Game Boy Light, fantastic, with built-in light, only released in Japan. A student of mine brought me one when he was doing his internship there. So no, it's not that. Nobody? Yes?
I just looked it up. Yeah, it's 2 to the power 22.
It's 2 to the power 22. Here you go. I don't think this book is good for you. Beginning C++, that will probably be way too easy. Yes. In the book I bought, I see you can also download the PDF from it. So it's very nice. So the clock is a power of 2 as a programmer. That makes me happy. What also makes me happy as a C++ programmer, there's no I/O port instructions. The Intel 8080 had these annoying I/O port instructions, which you then have to map to intrinsic functions to call or something like that. As you can see, that chip is a subset of the Intel 8080, the Zilog Z80, and some own stuff they added. What they left out from the Intel 8080 is mostly that port stuff. Game Boy is fully memory mapped. Yay. That makes our lives way easier. It has the 8080 set of registers and some extra bit manipulation that the Z80 does, and some additional new instructions that should help with graphical stuff. Now, the system on a chip is super, super simple. Because of this, right, it's easy to understand what happens. There's a memory map you can take a look at. What's important to notice here, the bottom 32K, that's where your ROM goes. When you plug in your little cartridge, I brought one with me. Actually, I brought two. They're both Tetris. I own them. Don't sue me, Nintendo. I took the data out with this, so I'm allowed to make a backup of my own games. I think. Now, games are not limited to 32 kilobytes, right? It gets plugged into there. The upper 16 kilobyte are switchable by doing crazy stuff, by writing to some ROM address. So you write to ROM. There's a chip that you can put into the little cartridges that catches that and then switches to another bank. There are different chips for that, which is called memory banking. Yeah. So
Why so much unusable?
why is so much unusable? Oh, it has to do with it's not entirely unusable in this graph. Part of it is RAM that you can bring in you can bring in external RAM from your cartridge. It's not usable by default, right? So you see it says internal RAM. There's also external RAM. This is a choice you make when you build your little cartridge. Why would you have external RAM? A good reason would be if it's a backup with a battery, it would allow you to do saves, right? Good question. Actually, good question. I suggest you give it to one of the young guys. Although I cannot determine your skill level based on age, or your age based on looks. Okay, yeah. Even giving away stuff gets harder. Oh, wait. I also have this. Yeah, not for you, not for you, guy. Yeah, in Belgium we have a tradition of distributing alcohol to everyone, so that's how we make friends. Because we're really sad and have no friends. So the Game Boy, although it has this very limited graphical ability, it has 8 kilobytes of RAM. The NES only has 2. And so in a way, it's more powerful than a NES, and other ways it's not. It's not as powerful as a Commodore 64. Also, you never want to say something is more powerful than a Commodore 64 because the fans are going to kill you. The Commodore 64 is the best thing ever made. There's also VRAM. Interesting, the VRAM actually runs at another clock frequency. I'll say a bit more about this in a bit, but the main RAM runs at 1 megahertz. Well, 2 to the 10th hertz, right? And the whole processor is constrained by this. The VRAM needs to be a bit faster for the PPU that actually runs at 4 megahertz. Okay, excuse me. 2 megahertz for the VRAM, 1 megahertz for the normal RAM. Yeah. Okay. Yeah, we're quite a bit in, and if you want to know everything and all the details, there's this great talk by Michael Stahl. It's a couple of years old. He's very talented. So if you're interested in Game Boys, go listen to this talk. The link, you don't have to take a copy. It will be on the slides and on the PDF. I think I have to provide a PDF, but I will also provide the PowerPoint file on Discord, so you can look at my comments. If I put something in the comments that I forget to put on there. So yeah, we know a lot about the Game Boy now. Yeah, let's implement one. I have like 45 minutes left. How hard can it be? I mean, the guy who explains it in an hour, he talks really fast. I can type really fast. No, that's not going to work. So why is it not going to work? Well, look at this. This is the instruction set, the opcode. As you see, It's pretty filled. There's 11 missing. The gray ones, you see the gray ones, they are missing. Actually, good design. If you call one of the wrong ones, it crashes. Yeah. If you put in something in that does nothing or does something weird, you can bet on it that some game will use it for something. Eh? But that's not all. There's an instruction there. Well, yeah, I have a little bit of explanation what the colors mean. We're not going to go through each one of them. And also what the little numbers on the bottom mean. And it says something there about T cycles and M cycles. Here already starts a big discussion within the Game Boy technical analysts, fans. Is the processor a 1 megahertz or a 4 megahertz processor? The reality is, if you look at all the number of cycles each command needs, they're all multiple of 4. So internally, it's running at 4 megahertz, but every instruction takes a multiple of 4, and it's constrained by the memory that goes at 1 megahertz. So some people decided to simulate it at 1 megahertz, and this works rather well. So realistically, if you wanna make a start at the Game Boy Emulator, yeah, M cycle is gonna be good enough. Confusingly, T cycles are sometimes also called machine cycles. And M cycles are for memory. Let me break your dreams as aspiring emulator developers immediately. You cannot get there entirely with M cycles. This game requires and does incredible, tricky stuff that's including related to interrupts and so on. That requires you to have T-cycle precision. Suddenly, your mission has become 4 times as complex. Yay. There's something special also about instruction CB. So if you look at line C, column B, it says prefix. That's a weird instruction, prefix. Anybody know what prefix does? I'm not giving you that book. Yeah, but yes, it introduces another page, and that page is full. So there's 256 opcodes plus the 500 and plus the 245. That gives us a total of 511 opcodes. Whew. Yeah, annoying. Thank you. But you were technically right, which is the best kind of right. Come pick up your prize. Here you go. I'm out of prizes now. Unless somebody wants a slightly dated computer who blue screened this morning for the first time. Yeah. Oh, wow. I included the same slide twice. Okay. Oh. Well,
That's another 512 instruction.
yes. Fortunately, no. So, how are we going to get about it? Let's maybe take a toy example and implement that. A toy example. Let's just pick a game, see which instructions it uses, and implement that one. But which one should we pick? I'm really out of inspiration here. Damn, it goes slower than I thought. Mario, well, actually a good idea. Wow. There's actually a site online where you can make these things. I didn't go through the effort, but you can export it as an animated GIF or GIF, whatever you want. Yes. Again, we will not start a religious fight. So why pick Tetris? Well, it was a launch title. Anybody who's a bit of a collector of Game Boys has plenty of Tetrises. Has plenty of them. It was bundled with it. I own 8 Game Boys, and I think I own 6 or 7 Tetrises. So it was bundled. So that's convenient. To this crowd, I will not have to explain what Tetris is, I hope. For a project internally, I had to present it and I had to explain what it was. So here you go. You can read it in your own time. It's still hot. There's a great movie about it that was released recently. Actually, Tetris for Game Boy was re-released as a game for the Nintendo Switch Online. Totally not a money grab, but because it's such a good version. Okay. Now, really, why Tetris? Well, Tetris only requires M-cycle precision. Oh, that's good. That's good. M-cycle precision, that divides our job by 4. Only 284 of the 501 opcodes are used. That's also great. And the size is only 32 kilobytes. That's fantastic. If you open one of these up, one of these cartridges, one of these, I forgot the special screwdriver you need, but if you open one of these up, it's just one ROM chip. Easy to dump. Also nice, right? If you dump it to a file and you look at the size of the file, it's exactly 32,768. At least I think everybody recognizes that number. Interestingly, also, it supports the game link. So if you want to make your emulator more interesting, you can do that as well. I will wait until networking gets added to the C++ standard. So I'm not really holding my breath until that happens. So, okay, we discussed why an emulator, why the Game Boy, why does it have to be fast? Well, bragging rights. On the other hand, you know, the Game Boy runs at 59.7 refresh frequency for its screen. So it doesn't really need to run any faster. But if it runs faster, you can run it on lower-end hardware. It's also cool. But also, in my organization, the research team wants to use it for machine learning. If your Tetris runs 100 times faster than the original one, you can train 100 hours in an hour. That's a great advantage. And there's also something called the tag law. Does anybody know what the tag law is? Nobody?
Dinosaur?
No. Good try. Good try. No science fiction readers here? Read more science fiction. Of course, I made a backronym for it. It's a scientific project that I'm working on in my spare time. It's called the Tetris for Game Boy Logic and Version. And what do we want to do? We actually, imagine I give you this screenshot. The Game Boy, if you look at all its opcodes, does not really support random. Right? The random is generated based on when you push a button. So, given this screen, could I know what moves I need to make to get there? It's a non-trivial question. It's to do with reversible logic and Turing machines. It requires also a lot of brute forcing, for which I need a high-speed emulator. Okay. Why no sound? I didn't say no sound yet, but I'm telling you now, we're not going to do sound. Because you don't need it, right, for Tetris. Is that always true? Well, not always. There's one of those projects one of those homebrew projects called Little Sound DJ. And I have a student, one of my students called Patrick, he's in the audio major, and I play around with it. This is what he made. The screen you see, he ran it on a color GameBoy emulator, but also runs, it's one of those compatible to both. If you put in a color one, you get some extra color. So it's just a GameBoy cartridge, and this is what he made. I think you will all recognize it. It's amazing to me that such a small device can make such nice audio. We won't go into detail about the audio, but notice that only 2 of the 4 available channels are used. So if you want to port Doom, there's still channels left for your sound effects. So what are you guys waiting for? Go port Doom to the original game. By the way, that's not possible, unless you put really powerful chips into the cartridge, and that's kind of cheating. Okay, and then it loops. So for this game, it's not, well, it would be useful for Little Sound DJ. There's other games where it would be useful for. What does that mean, that sound? Well, it doesn't mean Zelda, but it's related to Zelda. It's either you discovered something, or in Zelda Link's Awakening, which is the best version of Zelda, fight me. I will die on that hill. It's also the sound that plays if you come into a room where there is a secret available, right? So if you ever want to write an AI that plays it, if it doesn't get an indication of that sound played, it's playing at a big disadvantage. Sorry. So that comes from this game, Zelda Link's Awakening. It's one of the greatest games of all time. All right. Okay, so yeah, we're gonna make this Tetris emulator. We're already limited our scope quite a bit. We're gonna be using it. We're gonna be using it for simulations and AI, because you can't sell a project nowadays if it doesn't have the words AI or machine learning in it. But if you want to play it, I need to make some kind of an interface. Now, if you take anything away from this talk, check out the OLC. OLC stands for the One Lone Coder, the One Lone Coder Pixel Game Engine. The guy has a YouTube channel. It's actually a very user-friendly game engine that's a single header include. Especially for those of you who teach, like me, what you suffer with students if they have to install libraries and DLLs and project settings, and that's a nightmare. Single header include, it's nice. It also detects what the platform is. It will compile to Windows, to Mac, to Linux, to WebAssembly if you kick it a bit in the butt. There's actually a site called PGE Tinker, which is like Godbolt. Do you guys know Godbolt? Yeah, I should call it the Compiler Explorer, but nobody does. It's a lot of typing. Where you can actually run graphical applications right in the browser, interactive graphical applications. So once your Game Boy emulator works, you can actually upload files to it and then include it, and you can make an online playable version. If you do that with some of those homebrew games, not with an original Nintendo game, because that's totally not okay. Okay, since I talked about it, let me show you what an empty One Lone Coder Pixel Game Engine program looks like, and it looks like this. Just an include, you do the define because this is the main place where you include it. You define some class that inherits from Pixel Game Engine. You override a constructor. You create a function onUserCreate, onUserUpdate. And then in your main, you make one of those objects, you construct it. The parameters, that's the size of your canvas. The two following numbers are multipliers on your pixels. If you run it like this, every pixel will be a 2 by 2 on your real screen. Very convenient, by the way, if you write a GameBoy emulator. A GameBoy on a modern screen, the 160 by 144 pixels, that's like this, right? So it's very nice. So yeah, that's what we're going to use. So I need to decide on an API. That's what I'm going to be stuck with for a while. So I'm going to make it simple, right? Yeah, I have some ROM name. Why do I have a ROM name? Just going ahead a bit. The ROMs contain the name of the game. So if you upload the game, you can actually get the name from it. So that's convenient. I want to store that. Something to start the emulation. Some get name function. Something for getDisplay, which returns a pointer to where you can find the data. Some vector of bool, and then how many frames you want to run the thing, and then some values that I want to define. Now, I see you all cringing with what is this guy doing with his raw pointers and stuff. That's not the kind of interface I want to make. But I need to give that interface to the AI guys. The AI guys also told me, oh, that's great, 160 by 144. And I told them, yeah, and 2 pixels per color because it's only 2-bit color. No, we want a byte per pixel. 6 bits are lost. There you go. Same with the buttons. We all think the same thing. 8 buttons, 1 byte. Just set the bits of the buttons that are pressed. No, they want an array of bools. Yeah, that's unfortunate, but here we are. Yeah, that's the content of the Tetris ROM. You can analyze that header. There's some interesting information in there. Okay, so. Let's just do wishful thinking. An important technique when we write code is wishful thinking, right? I would write it like this if I had this library, and then afterwards you go write the library. And then you also imagine which parts you would like to have. So I'm starting this application, right? I have some emulator that I start up. I pass it the name of my binary. Now I start it up, and then yeah, here you see I created a win main. If I create a win main, then I don't have a little console opening, which looks better. And then I construct this thing. How would the main code look like? Something like so, right? The user updates. I get the buttons. I put them in an array. Yes, I know. I pass these on. Right? I check because even a very naive implementation will easily on a modern piece of hardware be 40 to 50 times faster than a real Game Boy. So you're actually, right, the 59.7, you're actually the 0.0597, you're actually waiting for the next update. Okay. So what does it look like? Well, if you run it, it looks something like this. And if you're thinking, Tom, wow, you have great colors. Yes, I do. These are the RGB values that you need to get pretty close to the original Game Boy. Again, depending on the screen you have. And now we come at a crucial point in this presentation. The question is, how much of realistically of this emulator can we write right now together? The reality is not a huge amount. I'm a teacher. I want you to write a GameBoy emulator. I hope you're all enthusiastic now and thinking I'm going to go home and write one. Join the leagues of people who have. If you do, please send me a mail. I still have time left in my presentation. What I'm going to do? Well, remember what I said earlier with Tetris? It was a toy example. Now even the toy example maybe needs a toy example because we're going to do something. My guy is going to be really mad at me. Tom showed up and showed nothing. That's terrible. How many of you have already written an emulator? Not a lot of you. So that's for those who already have, this will be kind of a refresher. For those who haven't, I think you will find this interesting. We'll start up with I need some kind of hardware to emulate something simple that I like. I want to try something else that I usually tell my students not to do. Let's see how well that works. I will try to switch. Yes. Again, don't worry about the link. The link you can find on the slides. So there's this online little emulator. It's also based on the 8080. So the things we are learning are not lost. It's a simplified version. Look, the RAM is only 256 bytes. I have this little assembler here. A program has been written for us. Let's improve it a bit. Like so. If I click assemble, it actually assembles it and downloads it into my memory. And it's nice, it's also linked. I can see, oh, this bytecode is linked to this instruction and this one is to this instruction. Halt is apparently a 0. A push does this. The color, the orange color right here indicates where the stack pointer is currently going to write to. This gray area, if we write to this zone, to these memory addresses, then it will appear on our display, which is memory mapped. Again, memory mapped stuff, that's cool. We also like that. Here is our output. So let's see what it does and run this. It's pretty slow. Oh, an H appears in my screen. Of course, it's over-engineered to do something such as simple, but I like the Hello World example because it has a function call. It pushes stuff on the stack, so it can come back after it and restore registers A and B. So this is all very nice. And there we go, our program worked. Now this is realistic. This we can write and improve on and make the world's fastest. By the way, how do you get the world to be the world's fastest at something? Or the world record keeper? Be the only one. Actually, I looked it up. Nobody is trying to make as fast as possible GameBoy emulators. Nobody cares if it gets 59.7, they're fine. Okay, so this looks good. If anybody knows a good technique for switching between presentation modes. Yeah. Yeah? Yeah. It's okay. It's okay. I have a special place in my heart full of hate for PowerPoints. The kind of hate you can only have when you use something a lot. Okay. Yeah. Here we are. Yeah, this is a little schematic to explain. You might have noticed there was a bunch of numbers there that weren't used. Those of you who read fluid ASCII, which is everyone, I guess, this is just hello world, right? And this 1F, 0F is actually a jump instruction, which will jump to the next instruction. Okay, and then the stack will grow upwards. So let's look at our hardware. It's an 8-bit controller. It has 256 bytes of RAM, 24 of those are shared with video. See, very modern system. 4 general purpose registers A, B, C, and D, a stack pointer, an instruction pointer, 3 flags, and the simulator runs up to 16 Hertz. I know. Has science gone too far? I think so. So there's a bunch of operators that are available there. Move, which is a terrible name if you think about it, because it's really a copy. Define bytes, add, increment, decrement, multiply and divide, push and pop. There's and or, XOR, not, shift left and right, call to call a function. It actually pushes the address of the next instruction onto the stack, right? So and when you call return, it pops that from the stack. So you have to be sure you keep your stack. Okay, halt stops the program. There's also an unconditional jump, a compare, and then a bunch of conditional jumps, right? If you do math, the target operand always has to be registers. For math, multiply and divide, always target register A. Does anybody know why that is? Yes? Yeah, it's the accumulator. And why do they only have one accumulator? Yeah, because F us, that's why. Yeah, but when we say move, there's more than one move. It's not just one opcode, right? So let's see how much assembly you remember. I'm trying to do stuff here. Putting something between square brackets means that I'm using it as a pointer. Which of these instructions mean nothing? Are useless? Yes? Yes. That makes absolutely no sense. You cannot move something into an immediate. That was the easy one. See, you really deserve that book. Well done. There are 2 others. Memory to memory doesn't work. On most architectures doesn't work. There are exceptions. But now if you look at the bytecode, all of these are different-ish numbers, right? A move to a register is instruction 6. A register move is instruction 1. To an address is instruction 8. Why is that? It's pretty obvious, but why? Yes?
There's bit codes in the opcode.
Yeah, and it's just, and for the CPU, it's just numbers. How does he know the next parameter, which is a 1? Does it mean register B? Does it mean a 1? Does it mean the thing at address 1? So we need a lot of opcodes. Okay. So what we're going to do is, we're going to take, and I thought I didn't have enough slides. Yeah, well, I have to show what. We're going to take that program in memory and put it into our C++. This I will not talk about. Yeah, the thing is, if you copy this, you get some numbers. With the regex, you can transform it. That's nice. No? I'm sorry. Let me switch screens again. Yeah. Okay. So let's go for a first super naive implementation. All the code that I show, the links are on the slide, so you can look at it. If you feel annoyed by this code, good, you should be. It's terrible code. It's bad on purpose. We're going to improve it as we move along. I have some class CPU, has some memory, and look, I have magical constants and everything. Some stack pointer initial value, somewhere where my ASCII display sits. I have a whole bunch of opcodes. I've removed all those I don't need. If you look at the list before you do that, it's way longer. There's, I think, in total around 89 or something. So we just made some little enum with the instructions. Here we have a load program. Oh, by the way, if you use C++23, another place where you can avoid using a raw for. Students use enumerate, love it. Also structure bindings, they're great. And then executing an instruction. Well, I take whatever my instruction pointer is pointing at. Initially, it points at 0. I switch it. I throw it through this huge switch. Depending on which instruction it is, I have to take one or more parameters and do something with it. Look, I've been programming in a safe way as well. I have a search there. Safety first. Look at it, it's great. It's an example. And if I have an unknown instruction, I will also throw something. Look at this, it's beautiful. And then I have some display state. I try to reproduce, but I want to do it in the console log. I try to reproduce more or less what the graphical thing here makes. That's actually pretty convenient when you're debugging it. If you try to replicate this work, it's actually quite interesting. You can put waiting for a key inside this while, and every time you can press enter, and you can do it on the emulator as well. In the emulator, you can, let me show that. You can just step through instructions and see how the state changes. See the instruction pointer change. So it's very easy to debug like that. Well, a bit annoying, but still very easy. So I load in my program, I run it. My final state says, hello, CppCon. Yay, step 1. We're doing great. I'm not doing great on time. Yeah, I'll have to turn it back on again. I have discovered the best thing you can do with PowerPoint is turning it back on and off again. It's a bit slow. Okay, so first rule of programming, don't repeat yourself, right? If you look at that code inside that switch, won't look at it again, but there was a whole bunch of repetition there, a whole bunch of things we typed over and over and over and over. So that's the dry rule. Everybody who teaches knows students don't work with the dry rule. They use the wet rule, which is write everything twice, or write every time, or we enjoy typing, or waste everyone's time. We can actually improve the code a bit, and I'm going to skip on this version. The first thing I do to improve it, I use dry. I have some function calls in there. Those function calls are also annoying because I change global state inside those functions. They're actually pretty dangerous, right? I take a parameter and I change the instruction pointer. So then the next thing I would tell you, you shouldn't do that. Don't do that. And but interestingly, even just adding dry and exceptions doesn't affect speed at all. Sometimes I have to fight against a lot of prejudice about stuff like that, but doesn't have any effect at all. I think there are people in this room who know a lot about it, way more than me. Thank you for making us all look bad. So yeah, let's make a class. It used to be annoying in Godbolt to make a class because then afterwards you had to take your CPP and HPP files. I agree with Jason. I saw you're 100% correct. They should change the guideline. So yeah, but you had to put it all in one file. But now it supports CMake, which is great. So you can just spread your class over several files. I'm not going to go through all the code because, again, I don't want to go over time. Oh, here I was showing how you can avoid naked force. Interestingly, switching to a class makes it faster than the terrible code we saw before. I have no explanation why. If anybody can help, the code is there. Maybe I made a mistake somewhere. I also tried making the object on the stack, making it with new. I know you shouldn't, but just for try, and that's the same speed. It seems to. I have no explanation for this. Again, thank you. Yeah, and while I was preparing these slides, I was going to show everything with Quickbench because I love Quickbench. I don't love that you have to put everything in one long file, but I'll live with it, especially since I was taking a toy example. Yeah, and it stopped working a couple of days ago. And then it started working again now that I'm at the conference, but I didn't have time to rerun everything. Besides, in the meantime, I had written my own little benchmarking template. Oh, wow, an excuse to use a require. I can require that you pass it an invocable. I run over the thing several times. If it's too small, you can also say inside that for loop how many times you need to run it. I time it, then I sort it, and I'll calculate the average and the standard deviation. I don't think this code is very surprising for anyone. We've all written this code in one form or another, I guess. Okay, so I had a kind of a basic version that kind of looked good. And I had a header file and a CPP file, 2 header files because I had the benchmarking header file as well. Yay. So now I'm there. How can I make this faster? And a lot of the new C++ is about let's do things at compile time. And I was optimistic and looked at it like Columbus looked at the shores of America. Function pointers are const expr. That's actually weird the first time you hear it. But it's to do with the fact that there's 2 things that we call compile, and one is part of the other, and it's not a recursion, and linker is also compile time. Long story, we won't go into it. Anyway, you can have function pointers that are const expr, so I was thinking, what if I was going through this binary, and then instead of having to do the big switch, I would just make a list of function pointers with their parameters. That should be faster, I thought, naively. If you think, yeah, well, how are you going to load the file? Actually, I'm a huge fan of #embed. Some people tend not to like it. I think it's glorious. Yeah, thank you. Look, a Quine. Look at how beautiful it is. This Clank trunk, by the way, you can just, you have to set it to 29, I think. But that means you can load files at compile time. Great, so I had 2 things coming together. Everything was looking great. I could load the file at compile time. I had pointers to functions. This should work. This should work. I should be there. So, yeah. I needed to find a way to take all this information, and my first thought was I will make a map. Because if I want to execute an instruction, these instructions set at memory addresses, so I'll have a map with memory addresses and function pointers. That seemed to make sense. I also saw Jason has a movie about const expr maps. Yeah, so I thought, yeah, maps, it's going to be the way to go. So, again, long story short, I made it work. The code is on Godbolt. Right? I needed some helper functions, like, for instance, to count the number of instructions, but that's not that hard. You look at the first instruction, you look how large it is. I also needed some way to skip data. That's actually a real problem when you're going to be doing Tetris. You guys are going to be doing Tetris later. And one of the problems you have if you want to find at compile time which instructions you have is it's just bytes. Your art is also there. So you will have to have some way to skip some parts. Right? So I needed to have that as well. Built all that in. Yeah, a nice sprinkling of const-eval and const expr function. This one is const expr because I use it at runtime as well. and then I can initialize that map. I make kind of an array, and that array I use to initialize a map because I don't have const expert maps as far as I know. Execution is pretty simple, right? When I run through it, I just keep track of the instruction pointer. The instruction pointer gets the right function from the map and calls it. I'm sorry if I go fast, but I want to go through all the slides. Everything is available. Also, I'm available to talk to. My IDs are as you will see, not that great, so I need input. Yeah, here I did something complicated with this type. If you look at the code and you wonder why does he make it so complicated, that was before I did this little using where I had an instruction, which is a location and a core instruction. That made it more complicated in my templates. By the way, writing const eval stuff, that's a pain in the ass. I mean, the debugging part is a pain in the ass. The only feasible way I found, also help me if you found something else, is to make it not const eval so I can step through it and find my bugs. Okay, so I did that, and I was happy that it worked. That's always a good first step. When I did measurements, turns out it's slower than doing everything at runtime. Yay. But not one to give up. If I have a stupid idea, I persevere. So what about compile time and analyzing it? And instead of using a map that I have to fill and is also runtime, if I make a const expert array where I put these pointers at where they are, and I leave the rest empty. I waste some space, but space versus speed discussions, that's typical when you want to accelerate something, so I'd lose some space. But it's 32,000, an array of 32,000, that's nothing on modern hardware, especially if you're talking AI. Those guys throw around gigabytes like it's nuts. So yeah, again, execution, if everything is in an array and it's const eval, is really simple. Because of array size, it needed to be a template. The nice thing is these three execute instructions take different parameters, so they can just exist in the same class conveniently. Who's going to look at the code, but we don't have time. Oh, a nice aside, something that's annoyed me for forever, and it's only been fixed since C++20, automatically deduce the size of an array, especially if I do stuff with embed. You can since C++20 by using stud2array and passing the type, because if you just make a stud2array and you just give it a type, it will tell you your template doesn't have enough parameters. Extremely annoying. I actually I'm not going to say I was today years old when I discovered it, but I was not long ago old when I discovered this, and there's a whole bunch of code that I need to change with this. So I did some performance measurements, and as you see, the runtime version 6 milliseconds, the compile time versions with the map 12, and the array version was an improvement, good, yay, but still 9. So failure, right? Failure, well, I'm an optimist, or stupid, or a combination of both. What I like about it is that the standard deviation of the last version that I tried is quite small, which tells me in the runtime version, probably, I haven't done enough analysis yet, because the example is small and you cannot get, I will have to try this since it's promising on the full GameBoy emulator. But the standard deviation is the smallest in that last version. So I am guessing that the length of what you do for each instruction has a huge impact. And since the Game Boy does much less trivial things, right, when it's writing to PPUs and setting up interrupts and whatnot, I am thinking / hoping / stupidly believing that this will help. Okay, the last version we discussed is there as well. I also, it's kind of hard to read. I also made with just the instructions, we had 3 nested loops. So I had something that ran for a long time. And I put in a little counter in one run, so I knew how many instructions that was. It's about 5 million instructions, 50 million instructions. It does it in 200 milliseconds. So on my machine, I can make this little processor run at 250 MIPS, which is okay. It's only a 3 gigahertz machine. Okay, and I have 3 seconds. Thanks everyone, the CPP people, you are great, the organizers, as well as the people who are here. You who were watching this, you've all been great. My colleagues who always encourage me to do stupid stuff because they think it's hilarious. Students and former students are actually a great inspiration. They show me that I'm not the most stupid person in the world. My wife and son for always believing in me. This is a picture of my colleagues, so I brought them with me. You see, they're all weird, but we teach game development. What do you want? I have a last slide for questions. I called my son 2 days ago and I told him, I'm a bit nervous. These smart people are going to ask questions. I'm going to get stuck. And he gave me some advice. Keep in mind, this is literally what he wrote to me in a Skype chat. He's only 11 and he's not native English speaker. So, are there any questions in the...